Good evening, everyone. My name is Nakawe and this is my presentation of integrating the Allison Diploma in AI Fundamentals with my team project, which is the Smart Crop Recommendation System. So our first module is looking at the history, trends, and the future of AI. So the first module gave us the context for where our AI is today. It started with symbolic rules, just rules based on hard-coded rules, and it went through periods of doubt. For example, the AI winters and was reborn with the power of data and machine learning. And for my project, this history is crucial. Our system is not an old rule-based expert system where we manually code something like, if nitrogen is low, don't plant maize. Instead, we situate our project within the modern trend of machine learning. For example, we use algorithms like the random forest, the XGBoosts, to learn the complex and nonlinear relationships between soil data and successful crops from thousands of historical examples. So this allows a system to discover patterns we might not even have thought of to code. This connects us directly to data mining. The evolution of AI mirrors data mining's own shift from simple association rules to powerful predictive modeling, which is exactly what we are doing. And our intelligence that we're using here is the logical mathematical intelligence to calculate the probabilities and the outcomes of the numerical data. And when you look at our philosophy, there's strong AI versus weak AI. Our project is a perfect example of weak AI. It's a powerful tool for a specific task, but it does not understand what soil or farming is. So it has no consciousness or general intelligence. It is just brilliant at pattern matching at its own domain. So when we look at our second module, which is Introduction to Problem Solving in AI. And this module taught us that AI breaks down the problems into three components, which is the state, operators, and the goal. This framework is the bedrock of AI problem solving. It's the basis of solving a problem in AI. And when we directly link this to our project, the smart recommendation system, smart crop recommendation system, the initial state is the raw input data. For example, the nitrogen, the phosphorus and potassium levels, the pH, the soil, the location, the weather, and the data. That's the initial state. And the goal state is a clear and actionable crop recommendation. For example, plant maize, for example, plant this, or apply this fertilizer. And then the operators are the mathematical processes for our machine learning model that transform that initial data state into the goal state. This framing is powerful because it shows how a business problem, like what should I plant, can be solved. So this connects us to our data mining link. We have framed a classification problem, for example, a state space search where the AI searches through the possible crop states to find the optimum. Our AI searches through all the possible crops through its data, and it searches for the best one based on your input. And this made me consider the frame problem. So how does our model know which parts of the state are relevant? It knows to focus on just the NPK values, the pH, the location, and the inputs, but it might ignore a crucial and measurable variable like a specific micronutrient. This is fundamental limit which we always have to be aware of. This brings to us a question: can our AI ever truly think or know what is relevant to us? And our third module, which is problem solving by search. And we have two categories, that's the uninformed search and the informed search. And here we learned about different strategies from brute force methods to the informed search using heuristics. Essentially, educated guesses that guide the AI toward the goal. So, for example, while our model, if you link this to our project, while our model isn't a literary search, its decision-making process is similar to a heuristic search. So the model evaluates thousands of potential crop choices. It uses its learned knowledge as a heuristic function to instantly assign a probability score to each option. This allows it to immediately leave out the bad choices or eliminate the bad choices and focus on the most promising crops, just like the A plus algorithm finds the efficient path. So when this connects us to the data mining, we can use clustering to group similar farms together. This reduces the problem complexity by treating clusters as large states, making the search for the solution more efficient. Our model doesn't evaluate every possible farm individually. It just clusters them together and looks at them together, which makes it more efficient. The intelligence type you're using here is the spatial intelligence, which navigates the high-dimensional space of agriculture features to find the optimal point. So this process is like a simulation. The model isn't growing real crops. It's running a mathematical simulation of the possible outcomes based on history data to find the best result. Our fourth module is knowledge representation and reasoning. And this module covered symbolic AI and the first order logic using formal language to represent knowledge as facts and rules. As we can see, the knowledge representation, how knowledge is encoded. So an AI system can use its first order logic, a formal system using predicates, quantifiers, and variables to represent complex relationships between objects. And the rules and relationships are first order logic allows us to create a knowledge base of facts and rules about the world. The AI can then manipulate these symbols to derive the new conclusions. And when we link this our project that we are doing, the smart crop recommendation system, our project uses statistical machine learning, not symbolic rules, but then we can bridge the gap. The knowledge our model learns is encoded to its complex network of weights. However, we can use explainability techniques like SHARP to translate this black box into human understandable, like the first order logic rules. For example, we can generate a rule like if soil is 20, okay, let's use that one. If potassium is greater than 30 and rainfall is less than 1000 millimeters, then cassava, plant cassava. And this connects us to our data mining. So this is directly linked to mining association rules from data. Our model finds strong associations between environmental conditions and crop successes. The intelligence type here, linguistic intelligence using a formal language, for example, the first order logic, to express knowledge and rules. When you look at our philosophy, strong AI versus weak AI, this highlights the limits of formalization. Can we ever truly compare all the knowledge of an experienced farmer into a set of rules, which is probably not possible? So our model gets flaws by learning from data, but it's an approximation, not a perfect representation. So our AI is just a weak AI that doesn't know what is going on. It just approximates what a farmer would have thought or would have planted, but it's not the real representation of what should be done. And our fifth module is inference in first order logic. So inference is the act of drawing new conclusions on new facts from existing knowledge. So in symbolic AI, it's about logical deduction. Deduction, if the premises are true and the rules are valid, the conclusion must then be true. It sounds correct and complete. For example, all crops that require high nitrogen need fertilization. The fact is that maize requires high nitrogen. The inference, therefore, maize needs fertilization. And when we link this to our project, so our system performs probabilistic inference given facts and the rules. It infers the most probable crop label. For example, if sodium is high, potassium is medium, potassium is low, and the pH is 6.5, then the probability of cassava is 0.9. So from the known fact, the metric, and the knowledge embedded into the training model, the system infers the most probable crop label, which is not guaranteed access, but a statistical with a confidence level. And this connects us to the data mining, the intelligence type, and the philosophy. So the output of our classifier is an inferred label, a new piece of derived from the input features. The intelligence type here we're using logical, mathematical. The core of inference is logical deduction, even if it's probabilistic. And when you look at the Chinese room argument, the system can infer that cassava is the best without understanding what soil, cassava, or farming actually is. It's following synthetic rules, supporting sales argument that symbol manipulation is not true understanding. So our system can infer the correct crop. It can output the right symbol without a shred of understanding. It's manipulating data based on its programming, but it does not know what cassava is or what soil is. It reinforces that you have built a brilliant symbol, not a mine. Our sixth module is reasoning under uncertainty. So our sixth module is reasoning under uncertainty. And we know that the world is uncertain. And this module is focused on probability and Bayesian reasoning, which are completely essential for AI to handle incomplete, noisy, or ambiguous data. So the Bayes theorem updates the probability of a hypothesis. For example, crop is suitable as more evidence is acquired. And these are the probabilistic modules, the naive Bayes, a simple classifier based on Bayes theorem, assuming feature independence. Then the Bayesian networks, graph models that represent dependencies between variables and are used for complex probabilistic reasoning. And when we link this to our project, we know that there is a little uncertainty in agriculture. This is the reality of agriculture and its scope of our project. Sensor data can be imperfect. For example, the weather forecast or the soil can be imperfect. Our system must reason under this uncertainty. It doesn't just output maybe, but it outputs a probability distribution. For example, we can say 7% this is a direct application of the Bayes principles, allowing the farmer to see the confidence level and make an informed decision, but it doesn't give the final decision. It helps the farmer make a better decision. And this connects us to the data mining directly connected to the probabilistic classification models like the naive Bayes. Here, the intelligence type you're using is the naturalistic intelligence, which is the ability to make robust decisions based on noisy, incomplete nature signals, for example, soil readings, weather forecasts, and this is the naturalistic intelligence. And when you look at the philosophy, we can model uncertainty with probability, but we can never model all the unknown variables. There is always an element of risk, and our system is designed to be honest about that. When you look at module 7, which is planning. Planning is about sequencing actions to achieve a goal and advanced decision making. Planning involves generating a sequence of actions to achieve a specific goal from an initial stage. It involves defining preconditions. For example, what must be true for an action to be taken, and the effects, for example, how the action changes the state. The components, the initial state, which is the starting point, the goal state, the desired outcome, and the actions are what you can do. The plan is the chosen sequence of actions. In relation to our project, our goal isn't just to recommend a goal, but to promote sustainable outcomes. Therefore, it can generate a seasonal plan. For example, for action 1, plant legumes to fix nitrogen. Then the next season, after fixing the nitrogen, the legumes, for example, the beans, then the next season you plant maize into the improved soil. Remember, maize requires a lot of nitrogen. So this is a sequence of actions for a long-term goal. And this connects us to the data mining link. This can be linked to mining frequent sequences from successful farming data to suggest proven actions. The intelligence type is the bodily kinesthetic intelligence, which involves planning a sequence of physical actions, for example, planting, fertilizing, irrigating over time. And our philosophy here is a firm problem. So how does the planner know which preconditions are relevant for each action? For example, for plant maize, must it consider soil nitrogen? Yes. Must it consider the price of maize in the foreign market? Which is it may not consider, meaning its relevance is not complete. Then we have to include the decision making, and decision making involves choosing the best plan. Okay, choosing between different plans based on their expected utility by maximizing utility. And utility is a measure of overall benefit that balances multiple factors. The utility theory provides a framework for making rational decisions based on preferences and risk tolerance. So for our project, it's the rational choice, a rational agent chooses the action that maximizes its expected utility. This incorporates dealing with risks, trade-offs, and uncertainties. So for our project, our system doesn't just recommend a high-yielding crop. It makes a rational decision based on multi-factor utility, maximizing yield while also minimizing water usage, fertilizer cost, and soil degradation. It provides the optimal trade-off for the farmer's specific constraints. So we are not just maximizing yield, we have to balance multiple goals: high yield, the low water usage, the cost-effective fertilizer use, and the long-time soil health. So the AI's decision is a result of finding the crop that's best optimizes this multi-phase utility function for the farmer's specific context. Furthermore, we can plan sequences, actions like crop rotations as we looked at planning, to achieve long-term sustainability. We look at the data mining link here. It integrates prediction, what will the yield be, and association, what inputs are needed to and define decision-making framework. The intelligence side here is the personal things, balancing economic goals, that's the profits, with social goals, that's the life of personal, sustainability, community health, and intrapersonal, a farmer's personal risk avoidance. Showing arguments here. The AI's rational decision is a simulation of rationality based on the utility function. Is it really making a real decision, or it is just simulating a decision we told it to make? It's a powerful tool, but its values are only reflected in its design. It's a powerful tool, but its rationality is defined by its programmers and data, raising questions about value alignment. And our ninth module, and this module covered the core of modern AI, which is the supervised learning and the unsupervised learning. Supervised learning is learning from the labeled data. The classification, it predicts a category. The regression, it predicts a numerical value. For example, the random forest, the neural network. And then for the unsupervised learning, finding hidden patterns in unlabeled data. Clustering, which means grouping similar data points. For example, identifying soil types or regional growing. zones. For example, K-means clustering. When we link this to our project is a prime example of supervised learning. And we train our system was trained is a trained model on a labeled data set where the inputs are soil and climate data, and the labels are the historically successful crops for those conditions. The model learns the patterns that connect the inputs, allowing it to make predictions on new or unseen data. Unsupervised learning could first cluster farms to find patterns we hadn't even considered. When we look at our data mining link, this is the direct intersection between supervised learning, which involves classification and regression, and unsupervised learning, which involves clustering. The intelligence type here is the logical, mathematical intelligence, and the naturalistic intelligence, which considers pattern recognition and applied to environmental signals. So the question here is, can our machine learning model surpass human agronomists in processing vast multi-dimensional data sets instantly? It already has a form of superhuman agronomists in processing vast multi-dimensional data sets. It already has a form of superhuman ability, but it lacks the holistic understanding and intuition of a human expert, meaning a powerful tool rather than a general intelligence. So in conclusion, walking through the Allison course provided, but the real learning came from actively connecting every concept back to my project. It showed that our smart crop recommendation system isn't just code and data, it's a practical embodiment of decades of AI research, from search and knowledge representation to reasoning under uncertainty and machine learning. It also gave me a much deeper appreciation for the philosophical questions and the limitations that come with building intelligence systems. Thank you so much.